Hi, my name is Jehan. In this video, I'm going to present to you about the effect of instrumentation failure modes on a fast jet aircraft lateral stability augmentation system. The aim of this project is to evaluate the effect of instrumentation failure modes on a fast jet aircraft lateral stability augmentation system. And the objectives are identify the natural modes of the fast jet aircraft, develop lateral stability augmentation system, identify the effect of an instrumentation failure, mitigate the damage when an instrumentation failure. Let's take a look at the lateral motion of the F-104A fighter aircraft. There are three major lateral modes of an aircraft. These are roll mode, spiral mode, and Dutch roll mode. First, let's look at the roll mode of the aircraft. The non-oscillatory, highly damped mode, which has a large real root for the linearized lateral equation, is called the roll mode. Roll mode occurs when an aircraft is disturbed by a rolling moment. A large angle of attack will be experienced by the downgoing wing due to the upwash, and a smaller angle of attack will be experienced by the positive wing due to the downwash, hence generating more lift force than the opposite wing. Therefore, this will generate less lift force, which leads to a restoring rolling moment as shown in the top figure. Using the equation in the middle, approximation for the roll mode can be made, from which it can be found that roll mode of the F-104A aircraft has a 1.115 second rise time. Simulations can be made using the bottom equation. The Simulink model for the roll mode is shown in the middle figure and the response in the last. From the above graph, it can be observed that the response of the F-104A to a step input from the aileron is agreed with the roll mode approximation. When the aircraft is disturbed by an aileron input, the aircraft starts to roll whilst increasing the roll rate until it settles at 10 radian per second. Let's consider the spiral mode. The non-oscillatory, lightly damped mode, which has a small real root for the linearized lateral equation, is called the spiral mode. When a side slip disturbance is occurred to its balanced position, the side force will be created by the vertical tail due to the incidence angle created by the incoming airflow. As a result of this side force, a yaw moment, which leads to a different relative airspeed across the wingspan, will be created, and more lift will be created by the wing that moves forward through the airflow than the wing that moves backward. Hence, a rolling moment will be created. Moreover, a side slip will be created by the weight component acting on the lower wing. Combination of these motions, yaw motion, roll motion, and side slip, is called the spiral mode. Restoring moment will be created due to the dihedral effect and the vertical stabilizer lift force. Approximation for the spiral mode can be made using the equation in the middle. From that, we can get a rise time of a 22.25 seconds. Simulation can be made using the bottom equation. The Simulink model for the roll mode is shown in the middle figure and the response in the last. From the graph, we can see that the response of the F-104A to a step input from the aileron and rudder is tallying with the spiral mode approximation. Similar to the roll mode, when the aircraft is disturbed by a side force, the aircraft starts to change its direction and roll rate with the side slip. Since the side slip and bank angle were neglected, only yaw rate can be seen in the graph. We can see the increase in the yaw rate until it settles at minus 11.86 radian per second. Let's consider the Dutch roll. The oscillatory mode, which has complex roots to the linearized lateral equation, is called touch mode. It is a combined motion of yaw and roll which has the same frequency but out of phase. In here, yaw motion is lightly damped and slightly unstable. When a yaw perturbation is occurred, relative airspeed over the wing will be differ across the wingspan, which create a rolling moment. Due to the yawing moment, vertical stabilizer create a restoring moment which leads to yaw to oscillate whilst aircraft roll in the opposite sense. Approximation for the spiral mode can be made using the equation in the middle. From that we can get a natural frequency of 2.75 radian per second and a damping ratio of 0.041. Simulation can be made using the bottom state space model. The Simulink model for the roll mode is shown in the top figure and the response of the yaw rate in the middle and response of the side slip in the bottom. Let's talk about the stability of an aircraft. An aircraft is considered stable if it is come to its balanced position when it has been disturbed by an atmospheric phenomenon like wind gust, wind gradient or turbulent air. Stability can be categorized into static stability and dynamic stability. If a disturbed object has tendency to come to its balanced position, the object is considered to have a positive static stability. Similarly, if an object moves away from its balanced position when it is disturbed, the object is considered to have a negative static stability. If the object changes its position when it is disturbed but keeps the position without moving away from the balanced position nor comes to its balanced position, it is considered as the object has a neutral static stability. When an aircraft comes to its balanced position, reducing its distance from the balanced position over time, it is considered that the aircraft has a positive dynamic stability. In contrast, if the aircraft increases the distance from its balanced position over time, it is considered to have a negative dynamic stability. If the aircraft oscillate, neither closing into balanced position nor moving away from the balanced position over time, it is called neutrally stable. Let's talk about the stability augmentation system. When an aircraft does not meet the flying quality and handling quality requirements, the control characteristics of the aircraft are artificially modified using an internal computers to meet the required characteristics. This is called stability augmentation system. Stability augmentation systems uses sensors like gyroscopes, accelerometers, and magnetometers to calculate unnecessary linear and rotational movement to damp out those movements by using the aircraft controllers. The data that gathers from the sensors then feed back to the inertial navigation unit to calculate and use the required controller to stabilize the aircraft. Stability augmentation system reduces the workload of the pilot. In this project, modern control theory was used to design the stability augmentation system. Let's talk about the instrumentation that uses in the stability augmentation system. There are three major instruments in the stability augmentation system: gyroscope, accelerometer, and inertial navigation unit. First, look at the gyroscope. Gyroscopes has three major varieties which are mechanical, optical, and electromechanical system, which is called MEMS. Mechanical gyro works on the principle of conservation of angular momentum, and the optical gyro works on the Sagnac effect, and the MEMS gyro works on the Coriolis force. Now let's look at the accelerometers. Accelerometers also have three major varieties, which are mechanical, piezoelectric, and capacitance. Mechanical gyro is simple mass damping system, and the other two are MEMS accelerometers. One uses piezoelectric material to change the voltage of the sensor, and the other changes its capacitance when moving. Let's look at the inertial navigation unit. Inertial navigation unit is the onboard computer for the navigation and stability augmentation system. Let's look at the lateral stability augmentation system for the F-104A aircraft. First, look at the roll mode. Characteristic equation of the roll mode was changed by using the state feedback to meet the level 1 flying quality. A state estimator was designed to work parallel to the real system but faster than the real system to correct any errors. This system then digitalized so that it can be changed in the future without changing any hardware. Let's look at this spiral mode stability augmentation system. Characteristic equation of the spiral mode was changed by using a state feedback to meet the level 1 flying quality. State estimator set to have a time constant of 5 seconds. Then the system converted to a digital. Let's look at the Dutch roll mode stability augmentation system. Similarly, as other two, analog system was created to meet the required flying quality, and then a faster estimator and a digital system was created. Let's look at the errors associated with the analog gyroscopes. First, let's look at the constant bias. The constant bias of a gyroscope is the output value of the given that gives in even when there is no rotation on the system. This is due to the friction in the moving parts, temperature gradient. This can be overcome by calculating the average gyroscope output when there is no rotational motion to the known temperature ranges, and then subtracting the value from the output of the gyroscope. Constant bias can be simulated by adding the bias block in the Simulink library to the output signal of the rate gyro. Now let's look at the gyroscope drift. The gyroscope drift consists of two components. One is an angular random walk and a slowly increasing value. What happened to the output signal of the system when it is subject to the gyro drift is shown in these graphs. Gyroscope drift can be removed by monitoring the position relative to the gravity of the aircraft using the accelerometer feedback. GPS can be used to monitor the position of the aircraft over a certain period and calculate the gyroscope drift. Let's look at the white noise error. This is an error that could occur due to the vibration of the aircraft structure. This could be wing fluttering, engine vibration due to any moving part of the aircraft, or due to aerodynamic forces, elasticity of the aircraft, deployment of any control surfaces. This could be analyzed by testing stage of the aircraft life and use those calculated vibration disturbance to reduce the white noise error by subtracting those noises from the IMU for known and experimental situations. Let's look at the quantization error. Quantization error is a result of the analog to digital conversion. When a sample analog signal falls in between two signal steps, the analog value takes the nearest digital value, and the system becomes unstable. After this project, the stability augmentation system can be developed to work on any altitude and any speed. Therefore, more productive analysis can be done on the errors. More tuned state estimator can be developed. A proper test and experiments can be done to check the errors of the instruments. Thank you.